So good afternoon, everyone. Thank you very much for joining us for this webinar. We are going to get into a presentation and Q&A at the end, but I thought to frame this, I was taking my son to school this morning, was walking him to the train, and I said to him, "What are you doing at school today?" And he said, "We've got a cricket tournament." And I did my best to discuss it, but it's far too technical a topic for me to cope with cricket scores. So we quickly moved on from that, and he said, "What are you doing today?" And I said, "I'm doing a webinar. I'm hosting a webinar on retrieval-augmented generative AI in real time." And he said, "What's that?" And I've always thought, if you can't explain something to a child, you can't really explain it at all. So I said to him, think about it this way. If you're trying to do your maths homework and you don't understand a question and you ask AI to explain it to you, and I had his attention at this point because that's a compelling business use case for him. You get it to try and explain your homework, but you don't really understand the answer, and it doesn't help. So you give it a second attempt. You ask it a better question. You say, "Can you explain this maths homework? And by the way, here's the last 2 weeks worth of material we've covered." And it gives you a much better answer because it's got local, relevant, contextual information. It's got information in your language that's up to the minute and useful. And he got it. He got the essence of it, which is we can get these things to give us better answers if they have relevant, live, contextual information. And thankfully, he caught the train at that point, so I didn't have to go into any more detail. And thankfully, I don't have to go into any more detail now because I've got two excellent people here to explain it to us. So from Quix, we have Merlin Carter joining us to explain how you do this data, how you provide this data in real time and how you productionalize it. And we have the excellent Zain Hasan with us to explain how all the clever AI vector search stuff is going to work around it to actually answer that question and fetch the most relevant data. So I will hand over to them. Merlin, are you there?
I am here. Thank you, Kris.
Please
Indeed.
take the stage and explain.
All right, let's go. So good afternoon or good morning, everyone. Welcome to this webinar. Thanks for coming. Before diving into any technical details, I'm going to briefly introduce myself and Quix, the company I represent. But first, about me. My name is Merlin. I'm a developer educator. My background is a little bit strange. I have a background in technical writing and product management. So while I haven't worked as a developer professionally, I have been coding creatively in my studies and as a sideline. So I studied art here in Berlin, and I specialized in media and net art. So that basically meant I needed to learn how to code in order to create sort of multimedia web apps, interactive installations, creative AI projects. And during that time, I also spent 10 years working for a company that was like an enterprise version of Grammarly called Acrolinx. And then I learned a lot about computational linguistics and natural language processing, NLP. And so today I'm still fascinated by that, by NLP, also traditional rule-based methods, but also AI, using AI to process language. But aside from that, AI image generation, physical computing using sensors, Arduinos, Raspberry Pis, creating art installations that respond to movement and what have you. So yeah, essentially I love finding creative applications for AI and data processing. And speaking of which, I just quickly wanted to show you one example. So this is where I worked with a team. We use climate data to generate stories based from the perspective of certain locations on Earth. And we analyze the mood fluctuations of the data sets and use trained custom models based on literature selected by a poet. And so it was based on the elements, earth, water, wind, fire. And so the stories were narrated in this particular tone that we used from the trained models. So it was a great way to give people more of an emotional connection to data. And that's kind of what I'm all about. And so, yeah, so about Quix, the company I represent. So Quix specializes in real-time data processing, processing extremely high volumes of data, because the product was initially developed at McLaren to handle massive data streams generated by sensors on Formula One cars, which is kind of like NASCAR if you're from the States. So they realized its broader potential. They decided to offer it as a product for other use cases besides just sensor data. And one of the unique selling points, I think, from their experience at McLaren is that they discovered that data scientists struggle to interact with traditional real-time data processing frameworks that are based on Java, like Flink and Kafka Streams. If you don't know what those are, don't worry, I'll explain them in a bit. But the only thing you need to know is that real-time data processing, this world is traditionally been Java-based and sort of managed by software engineers. And if you needed to do some kind of complex physics calculation on a stream of data, a data scientist might create a prototype in Python or MathWorks and then hand it to a software engineer. And they would say, please turn this into something that works in production. And then the software engineer would refactor it into Java and make it performant. But this handover can create a lot of friction, which is what some people call the impedance gap. And so to bridge this gap, Quix created this Python library called Quix Streams. It's pure Python and it's more familiar to data scientists. And then you can run it in a cloud platform called Quix Cloud. And it's a simple client for producing and consuming data from Apache Kafka, and also does fully fledged stream processing. And so the key thing is that it works with the concept of streaming data frames. So it's basically an interface that's just like pandas. So data scientists know pandas, they work with pandas quite a lot, working with tabular data, and the concept is the same. So in your code, you can almost replace DF, which is what you'd use for pandas, data frame, and just use SDF instead. But otherwise, the interaction is very similar. So anyway, that's the story of me, Quix, and real-time data, but we also need to understand vector search and this aspect of the webinar. So for that, I'll hand over to Zain.
Thanks so much, Merlin. First of all, I'm super happy to be here. Been working on organizing this webinar for a while, thinking about what would excite people and what we could show people at the intersection of real-time data and vector databases. So really excited to be here. I'm Zain. I work at Weaviate as a developer advocate. My background is actually in engineering, and then in graduate school, I got into data science. And then I've been both working in data science and teaching, so I really like public speaking. Probably the most important thing about me is that I'm very passionate about AI and the good that it can do for humanity. And I know there's a lot of people that are afraid of AI, but I'm not one of those people. I think it'll help us a lot. Okay, so with that, let's go into a little bit about Weaviate. I'll take the rest of maybe about 10 minutes to talk about how Weaviate works. But Weaviate was one of the very first vector databases that was created. It's founded in 2019, way before ChatGPT. It's an AI native vector database, and I'll explain what that means. But essentially, what we're doing is taking a lot of the modular AI technologies, the language model, the embedding model that I'll explain in a second, and we're bringing it into the vector database. We're about 70 people now. The slide is a little out of date, and there's some of the customers we have at the bottom there. So let me go into how Weaviate works. And by the way, Weaviate is fully open source, and we're a company that believe in open source as well. And so similar to Quix, we're open source as well. Awesome. So let's dive right into it, okay? If I ask you to do anything on the internet, you probably have to start with search, right? If I ask you, what do you want to eat? You'll have to search for food. If I ask you, what do you want to watch? You'll have to search for a movie. If I ask you, what do you want to buy? You'll probably go to Amazon and search for a product that you're interested in buying, right? So every aspect of our life starts with some form of search, right? So whether that's searching for movies, songs, information, even products, everything starts with search. Right? And so vector databases allow you to solve this problem of search. So right now, the issue is that if you go to a search bar and you type in something that you're interested in, let's say you type in, why do airplanes fly? The issue is that you might get keyword matches that don't exactly understand the question. You're interested in the physics, the dynamics of why airplanes fly, and you get back a link that has all of the keywords, right? But it doesn't necessarily explain why they fly. And so if you use internal search engines for companies, and so Google doesn't do this because they allow you to use advanced machine learning search, but traditional search, this is often a problem. Right? So oftentimes the keywords are misleading, and the vector database or the search engine doesn't understand the intent of what you're asking, nor does it understand the meaning of the objects that it's got stored inside of it. What we really want is a semantic form of search. We want search based on human level similarity. Imagine going to a librarian telling them, I want to know why airplanes fly, and they're going to come up and maybe bring up an article or a book that explains exactly why. And this is the type of search that a vector database can give you. If we dig deeper and try to understand how this works, imagine you've got a machine learning model that sits at the intersection of your data. And you can imagine this is all of the data that you have in your computer. It can be text documents, it can be images, it can be videos, audio files, it can be any multimedia. It goes through the machine learning model and it generates this vector. And a vector is just an array of numbers. It can be 1,000 numbers. We're going to take all of our data and we're going to translate it into vectors. This is why it's called a vector database. So that first article that you saw is going to go into the vector database, going to get turned into a vector. We're going to take the second article, we're also going to turn it into a vector. And we're going to take, in fact, every other article and every other object we have, and we're going to turn it into a vector. This is for us to read and understand, and this is for the vector database, the computer to read and understand and to search over our data. And so these are called vector embeddings. Now what we do is, on the right-hand side, imagine all of these dots are the objects that you've inserted, and including the two that we vectorized right in front of our eyes. Now what's going to happen is our query comes in. So this is what the user put into the search bar. That goes into the machine learning model, and that also generates a vector. This is known as the query vector. And you can locate this query vector in your vector space right there. So now what vector search and what a vector database is really efficient and created to do is find the objects that you have that are in the close proximity of your query vector. And so here, that's the NASA article that we just extracted. And so all a vector database is doing is taking all of your data, projecting it into vectors, plotting it out to understand what that means. And then you get a query vector and you find which objects are in the proximity of that vector. A really great analogy here is you go to a librarian, you tell them what you're interested in. They know where every book is stored in the library, depending on its topic matter. And they understand your question, and then they go out and they give you the top 5 books that might be able to answer that question. Right? And that's, in essence, what a vector database is doing. It's allowing you to search across billions of data points in real time, and it's bringing back semantically relevant material. And so in this webinar, we'll talk about a couple of applications of vector databases. And to set us up for those demos and for those applications, I want to explain a little bit about how vector databases can actually power those applications. So the first application we're going to talk about is improving e-commerce recommender systems. What are even recommender systems? Right? So we've been talking about search. I want to start off by differentiating search from recommendation. If you had a user who typed into a search bar basketball jersey, any form of basketball jersey would be a valid return object, right? You could show them this image, you can show them any one of these images, and it would be fine. This is search. Now, if we talk about recommendation, exact same query, a user comes in, walks into a store, asks you for a basketball jersey. Now, in order to recommend to them, you can't just give them any other basketball jersey, right? You kind of have to ask them, like, who are you? What are your preferences? Are you a fan of the Lakers? Are you a fan of the Celtics? What type of basketball jersey do you want? Right? And so if this is the person that walked into the store, out of these three, there's only one right answer. Right? So if you're solving a recommendation problem, it's very important for you to understand the likes and preferences of who's asking. Whereas in a search query, it doesn't matter who's asking really, because the thing that you return has to match with the query, not with the person that's making the query. Right? So here, obviously, the correct answer is that. Whereas if another person walked into the store and this is that other person, now the answer is completely different, right? Same query, different person, different answer. Right? And so in the case of recommendation, we need to know who's asking. We need to know their preferences. And so in a vector database, you can actually cater the search results to the person that's asking. Right? And let me show you how you can actually do that. Imagine if I ask you, what type of burger do you like? Right? You could explain to me that. You could take a text kind of description and just tell me this is exactly the burger that I like, right? Or you could show me an image, right? Or you could tell me, describe a smell to me, right? Or you could, you know, show me a commercial and I could take the audio of that, somebody eating a burger, right? And all of these kind of identify you and the perfect burger that you like, right? All of the text description, the image description, all of these can be captured into a vector to identify what type of burger you like, right? And maybe you want to describe to me the nutritional content of that burger as well. We can take all of this information and we can project that into a vector, and now this vector is unique to you and it captures what type of burger you like, right? And this is the power of vector databases. Anything, whether it's images, smell, audio, that you can turn into a vector using a machine learning model, you can then use to search and recommend to that user. And this is not, this isn't technology that we've had at scale in production before. Not only that, but you can also use a multi-vector representation where you can take the text description and project that into one vector, the image description, project that into a completely separate vector. And now when you do recommendations, you could say, take 70% of the image vector and only 30% of the text vector and use that to recommend burgers. And in that case, the burger that gets recommended will look a lot similar, and maybe the description is not as important. So that's the first application that we're going to talk about. The second application that we're going to talk about is Retrieval-Augmented Generation, as Kris mentioned in his intro. What I wanted to do with Retrieval-Augmented Generation is just show you a flowchart of how that works. So currently, the issue with language models is this is how everybody's using them. We ask them a question that goes to the language model, and the language model gives you a generic response. No matter who was asking the question, you would get the same response or a similar response. And the only thing that impacts it or conditions it is what was in the prompt. Right? What you can do to improve this experience is to give it relevant examples. Right? And so in Kris's example, he gave the language model 2 weeks or 2 months worth of maths questions, and that gave the language model context as to what they're studying in class. Right? And so that can be generalized, and you can give the language model any relevant information that has to do with that prompt or that potentially has the answer to this prompt inside of it. And the language model can now, before answering the question, read over the reference material, do its research, and then formulate a well thought out, customized answer. And so this is quite powerful because now the language model need not be trained on this material. It just needs to read it at prompt time, and now it understands it. Right? And that's a simple explanation of retrieval augmented generation. It's just providing the language model relevant context. Right? And so in our vector search pipeline, we talked about taking our data, passing it into Weaviate. The query goes in through the machine learning model, generates a vector, and we get out a list of results. Those list of results are now going to be sent to a language model to act as relevant context. And this is why people are using vector databases and language models in production together, and that forms the basis of their retrieval augmented generation tech stack. Another application that we'll talk about here is actually retrieving source materials from the vector database, and those source materials can be any multimedia. right? So here, your vector database sits at the intersection. It acts as the retriever, and then this scales up to billions of documents, right? This makes sure that the retrieval step can still happen at scale. And then your language model then generates the answer. Right? And the last thing that I'll touch on here is the really cool concept of multimodal RAG, where if you have the ability to store any form of multimedia into your vector database, anything that can be represented as a vector can be stored in a vector database. So here you've got images, audio files, video files stored in the database. Now the prompt comes in, and the vector database retrieves an object and determines that the closest object to this prompt is not a text object, but rather an image. Then what you can do is take that image, take that textual prompt, pass it together to now a large multimodal model. So think the GPT-4 Omnis, Google Geminis of the world that can understand both an image and a text. And now it can give you a customized response by looking at the image, understanding the question, and then formulating a text response. And this is the very cool concept of multimodal RAG that a lot of people are working on now as well. So with that, there's still this one question of how can you do recommendations over e-commerce platforms? How can you do retrieval-augmented generation if the data is not already inserted in the vector database? What if you've got a constant stream of data that's coming in? How do I keep my vector database up to date with that real-time stream of data so that these applications can be real-time as opposed to just insert once and then query over and over again? Right? And for this, I'm going to throw it back over to Merlin, who's going to dive into this topic.
All right, great. Yeah, thank you, Zain. Thank you, Zain. So you might be wondering why we are associating Apache Kafka with vector databases and what these two technologies have to do with one another. So I want to leave plenty of time for discussion. I don't really want to get into too much into the details around the mechanics of Kafka, but let's just say Apache Kafka is a platform for orchestrating real-time data. So think of it as a stream transport platform that moves data streams around. So you can subscribe and produce data to topics, which are kind of like tables in traditional databases, but technically they're more similar to log files that are constantly being appended. And so Kafka here is relevant because vector databases depend a lot on real-time updates in the case where you are constantly having fresh data coming in. And this isn't exactly a new problem. So I'm just showing some excerpts from an article from DoorDash, the DoorDash engineering team from 2021. And if you don't know what they are, they're an on-demand food delivery service, kind of like Uber Eats. And like all those services, they faced a constant influx of new vendors and products coming in all the time. And so they need to keep these search results up to date. And any delay between the new products and vendors and the search results in lost revenue because they're at such a huge scale. So DoorDash incorporated this latency issue. They used to update their indexes in batch, but they were just running into so much trouble. And they re-architected their system to use Apache Kafka. And so this enabled incremental indexing, which meant that they could update their index whenever new data was coming in. And so Kafka kind of acted as a pipeline, funneling streaming data into the vector database. And I think this problem is also very similar for vector databases. So yeah, DoorDash wasn't using a vector database. It was just a very simple keyword index, inverted index. But for vector databases, it's even more relevant, I think, because you have to ingest these complex vectors that can be computationally more resource intensive to index. So yeah, in the same vein, because it's so useful, because these recommendations can help to increase sales and revenue, especially in e-commerce, you also want to make sure that the latency between the data coming in and the search is also reduced, so you can narrow those margins. So I'm going to, for the sake of time, I'm going to quickly rush through some more of these slides relating to Kafka. But needless to say, all of these AI tools that people are building rely on a lot of different connections that stitch data together. And a lot of applications start out in this kind of point-to-point architecture where applications are making REST API calls, and it just turns into a kind of a typical spaghetti architecture. So if one API call breaks, then it can break the whole system. And so Apache Kafka can facilitate a pattern called the centralized event bus, where data is centralized, and then you can run processes on that central data store and stitch data together. And you do that stitching using an engine such as a stream processing engine such as Flink, Kafka Streams, or Quix Streams in Python. So, what exactly is stream processing? I'll just give you it very quickly. Stream processing engines often do some kind of continuous calculation. So the typical example maybe is a rolling average. For example, if you're doing sentiment analysis, or you want to get the rolling average for the last hour or the last 5 minutes, you would have to hold that data in a kind of running buffer in state and constantly shift the window forward in time at specific intervals so you can get regular snapshots of these averages. And how is this relevant for AI? Because it might be the kind of data that you would append to something else and then insert into a vector database. So perhaps you've got a user profile and you want to get their average of their purchase value or the average time spent browsing in a certain category. So you can enrich that data before it gets inserted into the vector database. And so, this is a slide featuring a diagram from Confluent, who are one vendor who produce and manage Kafka, but this can apply to any Kafka-based architecture. So in their example, they have lots of internal knowledge like support tickets and policies and what have you. And this use case was, for example, a customer trying to search for delays to their flight or asking questions about changing seats and what have you. So you can ingest this knowledge in real time and ping other systems like CRMs to get different information about the customer, and then send that as one package to the vector database. But Confluent and other platforms like this, they take care of managing Kafka, but you need systems to also run the processes and the microservices that do all this data orchestration. So, for example, you can run them in Quix Cloud or AWS Fargate, or Lambda is very popular, or Google Cloud Run. But whatever you use, you need some kind of cloud system to run these continuous processes. So that's the theory. I want to get into the exciting part, which is the demo use cases. So we have one more fun one, and we have one that's more applicable to real-time recommendations. So I will start with the fun one. So this is the pipeline that we're just going to look at. So what I'm doing here is I am transcribing what I'm saying as I speak using Speechmatics and sending it into a chunking process. It's getting live transcribed, and then we're inserting into Weaviate so we can ask questions about stuff I've just said. And as a bonus pipeline, we also have a parallel pipeline that is summarizing what I've been saying and creating embeddings and also inserting that into Weaviate. But in this case, we're just using Weaviate as a kind of normal database. So if I can jump to my screen sharing, then I can show you exactly what's going on. So what we're looking at here is Quix Cloud. It's the platform that I just mentioned, where you can run kind of serverless containers. And so each of these panels here represents a kind of serverless container, and the arrows running between them are kind of like they represent Kafka topics. So this is how the data is flowing through the system. And so here you can see I'm sending the transcribed speech to a Kafka topic in Quix Cloud. Remember, Kafka topic is kind of like a table. I'll show you what it looks like. Here we go. That's what a message looks like. So it's quite a small fragment that Speechmatic sends. And so what I'm doing here is I am just chunking it into slightly larger chunks so that we have better matching when we ingest it into the vector database. And then finally, we just ingest those larger chunks into Weaviate. And then, so what we can do then with the vector database is that I can ask questions about stuff that I've just said. So for example, let's ask, where did Merlin study art? Hopefully it knows. Yes. Okay. So these are publicly available. So we can share the URLs later, so you can try these out for yourself. And so the other thing that we have is also an app that does real-time summary. So this is quite handy for summarizing meetings for people who have joined meetings or lectures late and want to catch up on what the speaker has said. And this is a classic case for stream processing because you need to accumulate a time window of text to give it to the AI and say, please summarize this. There's no point summarizing tiny fragments. So that's what this process is doing. It's creating larger chunks for the AI to summarize what has been said. I think it's over, we've got 2 minute windows. So that's a real classic stream processing use case. And then just for fun, I'm creating embeddings externally using sentence transformers and ingesting them into Weaviate. So you can separate, if you want, you can deep couple embedding creation and use your own embedding model if you want, and then ingest it into Weaviate. In this lower branch, I'm just using Weaviate's native embedding integration. So that is the fun part. And I'm going to go into the second example, which is more recommendation engine based. If I can,
Merlin, maybe before we go into the second one, I think this is really awesome. While you were talking, this gave me an idea. So usually in the case of vector databases, when people talk about chunking, I've got all of my data right here, and I need to create semantically coherent pieces that need to be embedded and go into a vector database. Here you've got the opposite problem, right? You've got snippets of text, snippets of speech coming in as soon as they're being said, and they're too small to be put into a database. So you've got to wait a little bit until you've got something semantically coherent. That becomes, so you've got 2-minute chunks here as opposed to 300 character chunks. And then once you've got 2 minutes worth of data, then you put it into the vector database, right? So this kind of time-wise chunking is something that's pretty interesting that I think real-time ingestion allows you to do. Whereas, so that's something pretty cool, actually.
Yeah, I was wondering whether to do it based on time of the number of words that I'd said. But I just thought it's nice to have evenly separated time chunks when you're looking at the summary view. So my inspiration was like these sports commentaries. We say 2 minutes ago, so-and-so scored a goal. 3 minutes ago, so-and-so did this. So I wanted to have it kind of broken down time-based.
Yeah, it's pretty cool. And then one other question I had was, so imagine I had this running on my system as well. So now we've got Merlin's speech being transcribed, my speech being transcribed. And then you asked the question about where you went to art school or where I went to engineering school. How would it differentiate between the two speakers? That's typically a very difficult thing to do, right? Differentiating now Merlin speaking, now Zain speaking. How would you go about that?
Yeah, so I mean, in the client code, I can define a speaker here, and so in the payload, I've got speaker as metadata. So ideally, you don't really want to run it on your local machine. You want to run it on an integration with Google Meet. Like I wanted to use an integration called recall.ai. Actually, if we can just show my slides for a second, I can just briefly talk about that. Yeah, here we go. Yeah, so there's this tool called Recall.ai that integrates with Speechmatics, which is the API that I'm using. It's quite annoying to install the client library on everyone's machine who wants to participate. So you can just invite a bot to whatever meeting tool you're using, and they will expose an API, and then you can get the speaker information reliably. But in that case, you would just pass it back as metadata, whoever the speaker is. If we can just go back to just going to go back to the live screen sharing for a second. Here we go. So yeah, the speaker is in there, but when in terms of ingesting into Weaviate, so I have a hack where I make sure that it knows who it is by adding a little prefix like Merlin said, so that it when I'm doing the RAG, that it's doubly sure who said what.
Yeah, another interesting thing you can do in Weaviate is actually take the metadata and add a speaker column along with what was said, and then you could just say, let's say the query comes in and you have a way to identify that this query has to do with what Merlin said. You could just filter on the speaker, and then you only use your chunks versus my chunks. Right? So that's another thing that yeah. Awesome. Thank you.
I'm still learning Weaviate. So yeah, I didn't have time to get into advanced queries, but yeah, that's a great point.
Yeah.
Okay, so yeah, I'm going to go into the second use case. I just want to show the architecture diagram again, just quickly. So yeah, here we go. We'll go into using CDC to keep a vector database in sync with a product catalog. So this is very similar to the DoorDash example that I was talking about earlier. So you have a product catalog management UI. There's something called PIMcore, which is very popular. And let's just say you have a database behind that. In this example, I'm using PostgreSDB. And you want to keep your vector database in sync. As soon as new data lands in that regular database, you want to go through and process it, maybe enrich it somehow, and insert it straight into the vector database so that the search is immediately updated with new products. And so, yeah, CDC, change data capture, that relies on a log that most databases have, that they keep track of all the changes to the database so that they can replicate it if necessary. And so this is what we're doing with in this example. So I'm just going to show the final result first, because I want Zain to just give us a bit of background on the final UI that we're going to feed data to. So I'm just going to go back and share my screen again. Here we go. So this is like a demo e-commerce recommendation system that you built, right, Zain?
Yeah. Yeah. So the main idea behind this is to show the power of vector databases for recommender systems. Like I was explaining in my slides, if you have a user log into your platform and they're clicking around or they're putting things into their basket, you can use kind of the combination of the things that they've shown interest in to recommend things that are still not in their basket, right? So what we're seeing here is if the user clicks on or interacts with one item, it automatically re-ranks every other item and says, because you're interested in this, these are other similar items that you might be interested in, right? So if you scroll down to the bottom of this, yeah, so those are the items that are the most similar to that one item that they've interacted with. And here what we've done is we've taken these products, we've got descriptions of these products, and we're doing description-based recommendation, right? But you can also imagine if we were using an embedding model that could understand images and text, you could take the images as well as the text, and you can generate these multimodal embeddings and now do recommendations based on the color of an item. And so this type of recommendation due to live interactions, every time a user clicks an item, you fire off a query to the vector database. The query ranks all of the other objects. It could be thousands of objects. And now you have a short list of other products in real time.
Okay, so you're also updating your own vector store in real time?
No, so the vector database is not updated in real time. So we've got a
Okay.
catalog of, let's say, 10,000 items, and they're in the vector database. So the problem here is that if I get a batch of another 1,000 items, I would have to kind of insert it, and until they're inserted, they're not going to show up as recommendations here.
Okay, great. So let's get into the scenario that we're going to do for this demo. If we can just quickly go back to the slide. All right. So again, I thought I'd inject a bit of fun into this example. It's not very realistic, but let's just assume that this is something that's possible. So I live in Berlin, and Berghain is a very famous nightclub in Berlin, and people are constantly wondering what they're supposed to wear in order to get into this club. It's notoriously hard to get into. And so you have these TikTok influencers that are marketing to people and saying, oh, you need to wear this brand, you need to wear that brand. And so let's just say for this scenario that some really famous influencer has started recommending some brands that you need to get hold of. So you've gotten hold of these brands that everyone's buying to try and get into Berghain, and you've updated your product catalog and you want to make sure that it appears in search straight away for when the next TikToker goes live. So I am now going to go back to my screen and share it, and I've got my second pipeline here. So again, this is Quix Cloud with all these different services running. I'm running a demo Postgres database in Quix Cloud. Normally you wouldn't do that. You have it running somewhere else. But for the sake of simplicity, I'm running everything in the same environment. And what I'm doing here, instead of a product catalog UI, I am literally just using pgadmin, which is a query UI that you can use to manage your Postgres database. So instead of using a form to enter these products, so let's say we've got a new batch of products. I am going to ingest the first batch with a query. So I'm going to run an insert query on some hot new items that you can wear to Berghain that'll be sure to get you in. So let's just do that insert. Okay, good. Now, let's see what happened in the pipeline. So got the newest data here. Okay, so what's happened? It's immediately detected that there have been some changes to the database by listening to the log. And so we've got some details of the operation, the table it happened to, and the details of the actual entry that was put into the database. And this is the stuff that we're interested in. And so in the pipeline, it's very simple. I'm not using embeddings here, even though you can. I'm just going straight into Weaviate using Weaviate's embeddings. I simplify the data a little bit and then ingest it straight into the vector database. And so that should now show up in our search. So let's just try this out. So I'll just do a quick search for Berghain. See if there's anything there. Oh, look at that. Look at that gear. It's hot new items to get into Berghain. I'm going to ask the AI also if it has any recommendations. What should I wear to get into Berghain? And so this is like a AI-powered recommendation system. And yes, it has recommended the products that we've just ingested. Just to make sure that it works, let's just do it one more time. Suppose another batch comes in. I'm going to do an insert again. And let's go back to our pipeline, see if it's been detected. Yes, it has. Okay, so there's a few seconds delay, and then here we have our new items. And then again, if I go back to the search, let's see what we have for Berghain again. We have to close that. Go on there. Oh, we've got more items. We've got the luminous neon crop top now. So you can see how that is going to improve recommendations and reduce the latency, because as soon as things land in your product database, they're ready for recommendation. There's no delay because you're waiting for it to accumulate enough data in a batch or what have you. So
Maybe
yeah,
yeah,
go
one
ahead.
more thing that I can explain about the chat. So the chat part is interesting because um, it's also doing a mini RAG setup there as well. So when you ask it, what clothes can I wear to get into Berghain, that is doing a retrieval on top of the descriptions of the items that you've got, and then it takes those descriptions, passes it into the context window for the language model, and now the language model can give you an answer that's based on this kind of up-to-date catalog of information. Right? So this is also performing that retrieval step for you. So notice how there's a lot more items now because we just inserted more. Right? So that's
Yeah, exactly. So that can yeah, it's good. Yeah, it's and it also obviously understands from the history that I'm still talking about Berghain.
yeah.
Great. So I guess we can go back to the slides, and we've got 15 minutes for discussion. I don't know if anyone has any questions so far. I know that I've got a few questions, but let's see. Are there any questions
We do
out
have
there?
some questions coming in. I'm just going to need a moment to stop imagining you wearing that stuff at Bergheim, and then we can get into it. So one question that's come up is integration, which is the bane of all developers. If you wanted to start using this, say, with a graph database or one of the many other kinds of database out there, what's your integration path to the data stored in something unusual? Merlin, you can go first.
Yeah, I'm not entirely sure. Like, it depends on if that database has a log that you can use for replication. So, most of the mainstream databases like MongoDB or MySQL or SQL Server have these logs, um, because you need them in case of recovery. So it depends on, I guess, on the database. I'm not entirely familiar with Blaze Graph, but I would guess that they would have some kind of replication log. Kris, do you know Blaze Graph?
I've never heard of BlazeGraph actually, but I would
Right.
imagine that my first two places I would look are something like Kafka Connect for connecting lots of different interesting things to Kafka. That's
Yeah.
one way to get it in. BlazeGraph might have something that integrates with Debezium, possibly. That's another great way to read those logs. Zain, what about
Yeah.
Weaviate? Sorry, Zan. I keep calling you Zain, and that's terrible of me. Zan.
So,
Sorry,
No,
Zan.
no
Do you
worries.
What about on the Weaviate side? Is there much does it ship with database integration tools?
Yeah. So typically we do have connectors, like we have a Spark connector that allows you to take your data that you've got in Spark and you can dump it into Weaviate, and then that's what allowed us to integrate with Confluent. Um, but and then we also have integrations with other tools like LangChain, Llama Index. So if you're already using those, then you can kind of flip on the Weaviate switch and you can direct your data through there. Um, Probably the other way to ingest data is if you've got it structured in a JSON or something like that, right? Then
Mm.
you can kind of point Weaviate to it, and you can batch insert into Weaviate. I'm assuming that other databases, like uh, the questioner is asking about BlazeGraph, but you can also think about Neo4j or other graph databases like that. They probably have some universal kind of format that they can ingest data from. That's how we do it for Weaviate. So you can just take JSON objects and you can ingest them directly into Weaviate. And there's also an auto schema so that it'll directly take it and it'll embed it for you if you configure it appropriately as well.
Okay. Would you ever do it
yeah.
on the other end, instead of putting all the data into Weaviate, you get the answer back from Weaviate that says Postgres, this table name, this ID has the full details, and you just go and run a query after Weaviate.
Yeah, this is a question that we've been getting more of because imagine you've got a tech stack that predates vector databases. So you've got all of your data in Postgres, and now what you want to do is add a scalable vector search component to this. Right? So Postgres has PG vector, but if you want to add scalable vector search where you've got billions of objects and the vector search needs to scale up to billions of objects, then what you can do is because you can store the vector embeddings in Weaviate, you can also store the metadata that would allow you to connect back to the objects that are in Postgres.
Right.
Technically, you could say perform vector search and then give me back that particular property that allows you to connect back to the Postgres database,
Okay.
and now you can use that subset of kind of vector search approved candidates to now perform a filter on your Postgres database, and that's common.
Yeah. Yeah. These things often seem like they work a bit like a black box to me, but if you can actually get like structured, reliable
Yeah.
annotations on top of the magic bit, yeah,
Yeah,
that would work
yeah,
better.
for sure. So oftentimes the metadata, you can use the metadata to control the vector search, but not only that, you can use it to just return that metadata so that, let's say you get back 10 object IDs, and those object IDs can be used to locate something in a Postgres database. Then you just use the vector database for vector search, and then you can go to Postgres afterwards if that's where the remaining of your data lives.
Okay. Yeah.
Yeah, I hope you don't mind if I ask a follow-up question. That's
Yeah,
okay.
Please.
go ahead.
Yeah, so often when I talk about CDC, I see people saying, well, why don't you just use PG Vector, or like, these traditional databases, they now have their own vectorization add-ons, so you don't need to have the separation. But why would you like retain the separation? I think it's better to have like a database that specializes really solely in vector storage and retrieval, right?
Yeah, I think it completely depends on your application and what you want to, where you require scale. So, for example, if you've got 1,000 objects or 10,000 objects that you want to vector search over, and your Postgres can filter down into the realm of 10,000 to 1,000 objects, then you can perform vector search with pretty much anything. You don't need a dedicated vector database. If you want to perform vector search at scale, at millions of objects, tens of millions, hundreds of millions, billions of objects, then there's very few products like Weaviate that will allow you to scale up vector search to that scale and that have been tested and are used in production at that scale. So you kind of have to decide: do I need scalable vector search? Is the object count going to explode? And that's where using PG vector won't work, right? That's when you'll have to integrate Weaviate, and then PG vector can hold all the other data, but you'll have to go to Weaviate to do vector search and then throw the results back to PG vector, and then you can form some sort of filter on top of that. So that's mainly the one of the value props of a dedicated vector database, the scalability in the realm of vector search. Some of the other value propositions are also, like we talked about, if you have multimodal data, let's say I give you images and I tell you, give me other images that are similar, right? And that are semantically similar. There, if you've got a lot of those, you need scalable vector search. If you've got hundreds of millions of images, let's say we're talking about social media scale, all the images on Twitter or Facebook, there you need scalable vector search, right? And so there, something like a PG vector solution won't work.
Right. Speaking of scale and the choices at scale, gives me a way into another question we've had, which is, does this have to be Kafka? Could you swap out Pulsar? And why does that affect the pipeline? And is there a particular reason why you would choose Kafka, Merlin?
No, personally not. I mean, if as long as the stream processing engine integrates nicely with Pulsar, then yeah, why not use Pulsar? I think we're working on a Pulsar connector ourselves, though I'm not entirely sure what the progress is on that. But yeah, anything that can handle a high throughput of events would be fine. And I guess the point is, like, do you want to manage it? I think as far as I know, there are fewer managed Pulsar offerings than managed Kafka, but maybe correct me if I'm wrong. But sure.
Yeah, that's my impression too. It's like, logically, they're quite similar. It's when you get to the practicalities of scale and deployment that your personal circumstances are going to start really mattering, and then it becomes a depends question, right? Depends on what you need. I've got a question of my own I want to ask of Zain.
Sure.
While you were doing that demo, Merlin, there was a black T-shirt with a vinyl LP on it, which is something I thought I might click on that. And I thought, well, the response might be that it gives me 10 other black T-shirts, because it kind of assumes I'm an emo, and maybe one vinyl record player. If I click on the vinyl record player, it should now have enough historical context to say, oh, he's a music person, he's not an emo. My question to you, Zain, is how do we build up that context live? And then how do we store that context for when someone comes back to the website?
Yeah. So we have a module for this in Weaviate. It's called Ref2Vec, and how it works is when you log into the platform, you click on three objects. It takes you yourself don't have a vector, right? We have a user. When you log in, you don't have a vector. Your vector is determined due to the reference, using the reference to all the objects you've clicked, right? So if you log in and you click three products, it takes the vector of those three products and it combines them and it gives you that vector, right? And so that's how you do instance-based recommendation, where the minute you log in and you start clicking around, we can now give you this vector, which is the average of the vectors that of the products you've interacted with. And then another thing on top of it that you can do is, you can't do this right now in Weaviate, but this is a feature that is requested and we're thinking about implementing, is um, recency bias, right? So if you've clicked on a shirt and a pair of shorts 2 sessions ago, but you recently clicked on the vinyl, we can now track the timestamp of when that click happened. And then when you're retrieving, you can say, these are the three things that have come back. But instead of giving them equal weightage, we're going to prefer the more recent click. And the ones that were about 2 weeks ago, their preference is going to decay down. Right? So,
Right.
yeah, so that's
Yeah.
an idea that we're currently playing with as well.
So if I'm coming out of my cyberpunk phase and going into my emo phase, it will detect that change in tastes.
Exactly, and this is not just for this is relevant for recommender systems, but it is also very relevant for other real-time applications. Like one of the things that I was thinking of while Merlin was talking about the transcript application is, imagine I've got a constant stream of tweets, news media articles, and then on the other hand, I've got kind of stock price volatility. Is there a way that I could somehow rag over the tweets and the news media articles that are being dumped into my vector database, and then formulate some form of explanation of why this stock is being volatile or going up or going down, right? And so there, uh, recency bias is all important, right? Because something that happened 5 months ago is not going to affect the stock price now. It's more likely the thing that just happened, which is going to impact stock price action.
Right, yeah. What about persistence of that? Because if we're still on the example of clothes recommendations,
Yeah.
I've probably got, 10,000, 100,000 customers coming in for brief sessions, and then when they come back next week, I still want that reference that you mentioned to be swiftly looked up and assume they still have those tastes.
Yeah. So one thing that you can do is actually in Weaviate, you can have a multi-tenant setup where you can, the minute a person logs in, they are allocated a tenant ID. And then when they're clicking around, you can kind of insert objects into you can almost think of it as a private local version of Weaviate. And so now their index is only the objects that they've interacted with. And you can persist that. And so when they leave, let's say they're gone for a month, you can turn that tenant and you can, when they're searching over it, it's called a warm tenant or a hot tenant. When they leave for a month, you can turn it into a cold tenant and now you can take it out of memory. Now, when you see them logging back in, it's a, it's a process, but you can bring it back into memory. And by the time they're searching around again, their data becomes searchable again.
Nice. Yeah, yeah. Cool. I'm just going to check see if we've got any more questions coming in. Someone says that's very clever, so I agree. That's nice. Is that production ready, or is that a forthcoming feature? I didn't quite catch.
No, that's production ready. The multi-tenancy feature is something that we introduced about 6 months ago, and it scales up to millions of tenants. So if you've got a platform that has millions of users, technically one Weaviate instance can have a million tenants inside of it, and each tenant is the data is isolated, it's GDPR compliant, so you can use it for medical applications, financial applications. It's fully production ready.
That, given how primitive some of those, like particularly clothes searches can be, that I mean, I'm tempted to just hang up now and go and start my own fashion search business. So we should carry on with the seminar. I think.
Yeah.
I think that's all the questions we've got in the chat.
Yeah, I have a similar question about scale again. So you talking about the close recommendations, you made me think about, the viewing recommendations for Netflix or other platforms like that. And, they must be, I assume they're using some kind of vector database. I don't know. But, do you have anyone operating at that level of scale? I mean, you talked about scale earlier where, beyond a certain volume of data, you need something specialized like Weaviate. What are the industries or areas where you typically see that level of scale?
So the biggest scale that we see at is in e-commerce. They're also in kind of social media platforms. So there are some public customers that have kind of posted about using Weaviate. Probably a big one that I can share is Stack Overflow. And so when you look up questions on Stack Overflow, how does it know what other questions are similar? They're actually doing this semantic searching, and they're using Weaviate. And I don't know officially how large their data set is, but it's probably in the billions of objects that they're semantically searching over in real time to find out any relevant questions that close enough to the question that you've clicked on. Right? So in the social media space, in the e-commerce space, that's where we're seeing kind of multi-billion object scaled vector search. And so those are customers that are both open source and managed customers that are using Weaviate.
Gotcha.
We're pretty much at time, so maybe we should wrap up. I've got one last question for you, Merlin, which is, given how many people lose attention during long meetings at work, are you tempted to go and productionalize that system, which could easily remind you what's happening that you've tuned out of?
Yeah, I mean, there are obviously vendors that do that, like Otter or Firefly.ai, but what's more fun than building it yourself? Like all companies that I've worked in didn't want to use an existing product; they wanted to build it themselves. So yeah, I do want to trial it internally. What's that?
Spoken like a true engineer. All those other solutions, we'll build it ourselves. That's good. I love that.
Yeah,
If
exactly.
people want to build it themselves, is the source code available for that?
Yes, it.
Where do we
I
point
think
people to?
Yeah, there's a repo that I'll just see if I can post it in the comments. Where are we? Maybe someone else who has the repo link can post it in there. But yeah, it's in the Quix.io organization. So if you, here we go. I've got the repo link. I'm going to put it in the chat.
Cool.
Right now, that's on the develop branch, but it's there. Just waiting for the chat to accept it. Okay. It failed to accept my. But if
we'll get it into the description of this video in the next few minutes, I'm sure.
Yeah.
Oh, there it is. It's shown up.
No, that's the wrong one. That's the CDC. But
we'll get it. We'll get it. We can manage that level of technology given time.
Yeah.
So on that note, I think we should wrap up and let people go and play. Zain Hasan of Weaviate, Merlin Carter of Quix, thank you very much for taking us through it.